Hello everyone, I'm here to present our work, Probabilistic Debiasing of Scene Graphs. This work is jointly completed by me, Bachelor's of Research, and my advisor, Professor Chang Ji of Department of ACSC, RPI. Here is a brief preview of our work. We want to address the long-tail issue that exists in scene graph generation. For any image, for any biased scene graph generation model theta m, we generate the biased scene graph, we call it measured scene graph. We can decompose the scene graph into triplets, and then we can perform the within triplet inference for each triplet. The within triplet inference jointly infer the subject relationship and object, and the constraint optimization resolve the conflict that may exist in subject that are shared by different triplets. After the constraint optimization, we can get the inferred scene graph here, which improves the tail performances and decreases the head performances. Now, why do you want to debias our scene graph? We know the relationship label has a long tail distribution in scene graph dataset. And these long tail distribution create poor performance of the tail classes in state-of-the-art scene graph model. And the traditional debiasing is improve the tail classes and decrease the performance of the head classes. They also ignore the within triplet prior. In our work, we also want to debias the scene graph, but we want to incorporate the within triplet prior that will minimally hurt the head classes. The within triplet prior and scene graph dictate that the relationship of any triplet is strongly dependent on a subject and object. As you can see here, the man and surfboard, the relationship will mostly be likely on or hold. It will never be eating or flying in. Then we can capture this within triplet prior with a Bayesian network of 3 nodes. So the 3 nodes here are subject, relationship, and object. The subject and object are independent of each other. The relationship is dependent both on a subject and subject and object becomes dependent given the relationship. Under these assumptions, we can decompose the joint distribution like this equation here. Now we can learn the within triplet Bayesian network with the annotated triplets or with the augmented triplets. The augmentation is basically augmenting the triplet count of the valid triplets with the similar meaning invalid triplets. For example, here the man eating pizza, this triplet count is augmented with man consuming pizza or man biting pizza. Both with the annotated or with the augmented triplets, we can perform the maximum likelihood estimation of the Bayesian network parameter. Now we have the learn Bayesian network within triplet Bayesian network. We want to incorporate the evidence uncertainty into this within triplet Bayesian network. For each triplet, we can generate its subject, relationship, and object probability from an image with a Bayesian scene graph model that we denote here by M. Now we want to incorporate the evidence probability into this Bayesian network as virtual evidence. Here we can see the virtual evidence here. The virtual evidence nodes are added as a binary node to this subject, relationship, and object. Their conditional probability is specified from a likelihood ratio, and the likelihood ratio is basically dividing by the measured probability by the marginal probability. This scaling of the measured probability bolsters the tail classes and attenuates the head classes. Now with the well-defined marginal and conditional probability of this Bayesian network, we can perform the posterior inference. We can see this equation is the final equation here. Here these 3 terms, PMS, PMO, and PMR, they are the measured subject probability, object probability, and relationship probability. And the conditional probability is PR given also, and the marginal relationship probability is PR. The debiasing step is basically this. The debiasing is done in this step, and the within triplet storing part is done by this step. Here is the overview of our proposed approach. For any image, for any scene graph model theta m, we give the measured scene graph. We decompose them into triplets. We perform within triplet inference on each triplet. Then we perform the constraint optimization to resolve any conflict between the subject and object that are shared by multiple triplets. And then we can get our inferred scene graph. Here we give the reason why we didn't need the constraint optimization. Any triplet, as you can see here, they can share the subject or object. So after the WTI step, the subject or object may have different values, and then we need to perform this optimization, which will resolve the conflict and optimally choose one value for multiple instances. We do this optimization in two steps. First, we update the objects and we update the relationships. We evaluate our scene graph with recall and mean recall metric. And here are the performance comparison for all three settings, PRED class, SG class, and SGDET. We see that we can improve the mean recall, and also we see the recall is decreasing. And we do this for visual genome and GQA dataset. Now we can see the performance for all the classes. We can see the tail classes are improving significantly, but the head classes are improving or decreasing slightly. This is the typical behavior in any SGC debiasing work. Here we compare the performance with other state-of-the-art debiasing methods. We can see the other method, they have a very low recall compared to ours in the last row. And also we see that some of the other state-of-the-art method, they require retraining of the baseline model, but we do not need the retraining steps. The conclusion is that we debias the predicted scene graph with a less hurting of the head classes. We incorporate the within triplet prior and debiasing step through Bayesian network. We incorporate the triplet evidence with virtual evidence nodes, and we then resolve the conflict between subject and object through a constraint optimization step. Our method requires no retraining of the baseline models, and it can be incorporated as a plug-and-play module. Thank you for listening to our presentation, and thank you for your patience.